Welcome back to .NET Rocks. This is Carl Franklin.
And this is Richard Campbell.
And we're here for another Geek Out.
Yeah.
Hey, Richard, how's it going?
Hey, man, I've been reading Chinese to English translated technical papers on hypersonic technology. So I've been reading a lot of really bad English.
And you don't really read Chinese, do you?
No, so I had to get the translated versions. And, translators are only so good, especially when you're doing really high level, aeronautical scientific stuff. Mm-hmm. It's been tough slogging.
Well, I'm a little hoarse today because I did a gig last night with the Franklin Brothers Band and sang my hiney off.
Nice. First gig in a while?
No, it was the second one this season, and we were at a place downtown New London called The Social. Great room, very good sounding room, big, and we had the board from hell and the rig with the iPad and all that stuff and in-ear monitors, and we sounded so good. So I was just captivated by the moment and kind of blew my voice a little bit, so I do apologize.
The technology did not fail you.
No, it did not.
That's great.
All right, Richard. I do have something audio related for today's Better Know framework, so roll the music.
Awesome. All right, dude. What do you got?
Well, let's start with the problem.
Okay.
The problem is the headphone/microphone jack on most laptops today do not have line level input.
Right?
They're
amplified inputs.
Yes. So the difference between mic level and line level is a whole bunch of dB. And microphones operate at a very low level, and therefore they have to be amplified. And so typically the headphone jack is now a 3-band, 3.5 millimeter jack that has left, right, and microphone. And, a lot of headsets now have the microphone sort of built right in. So you just plug these things in, and that's what they're really focused on.
Right.
But we lost something. We lost the ability to handle line level signals. If you take a line level signal, like, for example, something that comes out of a stereo or some professional recording gear or a preamp that your microphone is plugged into, that line level is too hot and it overloads the system and it sounds terrible. So you may have noticed this, but in looking for solutions to this problem, there's a couple ways to go about it. You can get mic level to line level attenuators or, amplifiers that you put in line.
Right.
Or attenuators actually is what you want, because you have a line level signal. You have to attenuate it down to a mic level signal.
Right.
And those, I didn't have any luck with those. I remember I was telling you I was trying to find the right cables and stuff.
Yeah.
Just going nuts. And then I found this. Griffin Technologies iMic, the original USB stereo input and output audio adapter. So it's USB, and it does have 3.5 millimeter jacks for in and out. But guess what? You can switch line and mic level for the input.
Oh, it's got a switch right on the side of it.
Switch right on the side.
That's cool.
Yes. Now, this is really important if you want to set up laptops for different Skype channels, for example. So I've got a couple of laptops that I can use in the studio, and I set each of them up with a different Skype account and have their inputs and outputs mixed and matched and all that stuff in a mixer, but I still need to get in and out on line level. And this solves the problem for a mere $40.
Nice. You like it when the right product is just not that big a deal.
Yeah.
It just has to be the right product.
Exactly. And it supports Mac and Windows and just about every version of Windows and everything. So you don't really have to worry about somebody not having the right driver if they want to use it. I mean, you basically just plug it in. If you're online, it downloads and installs the driver and you're up and running.
Awesome.
Love it.
That's real cool, man. Good gizmo.
Yeah.
I think I need one.
Yeah, definitely.
It's just one of those things you want in your kit every so often.
You got it.
Yeah.
You got it. Oh, who's talking to us today, Richard?
I grabbed a comment off of show 1424. That's the March 2017 Geek Out about moon bases, which I think was fairly well received. And this is not a hugely complicated comment, but it's pretty direct to the point. It's from Penguin Man.
Penguin Man?
He says, "Hi, I'm 10 years old, and I love your Geek Outs."
Oh, that's awesome.
Hey, you know what? We love them too, Penguin Man.
Yeah.
Thanks so much for your comment.
That's awesome.
We're going to send you a .NET Rocks mug. And if you'd like a .NET Rocks mug, write a comment on the website at .NETRocks.com or via any of our social media. So we publish every show to Facebook and Google+. And if you comment there and we read it on the show, we'll send you a mug.
And definitely follow us on Twitter. He's at Rich Campbell. I'm at Carl Franklin. Send us a tweet. We wax our penguins with them.
I'm not going to go there.
No, well.
The Geek Outs need to be family friendly, I think.
Hey, what's the matter? Penguins need to be waxed.
That's do they now?
Yes, they do. Yeah. I mean, if they're living in the wild, they have that coat of oil on them all the time. But, domestic penguins tend to dry out.
Let's just think about this misinformation you're spreading right now, sir. On our enlightenment show.
I mean, if you got a penguin, they're going to live in your pool, right? That chlorine is going to do a number on the oils on the penguin's body. You got to wax your penguin.
We clearly need to do a Mondays. You just got this ranty itch to go right now, and you won't let it go. So, all right.
Well, where do we start with hypersonic? What does that mean anyway?
So a great question, and one thing that people fumble over one way or the other. And one of the reasons I'm talking about hypersonics right now is because they're kind of in the news at the moment. So we're talking about different flight velocities. Mm-hmm. So subsonic, which is below 0.8 Mach. Yeah. Remember that Mach is a measurement of speed of sound,
right?
Which actually varies with altitude.
Yeah.
All right. So 765 miles an hour is the speed of sound at sea level, but that speed goes down as you get higher.
Right.
And so that's why we care about Mach numbers, because the speed of sound hits up against the compressibility of air.
Yeah.
And so normal airliners, to fly efficiently, stay below in the subsonic range. The shape of vehicles has to change to fly faster than that, which is why we tend to only see that in the case of the military vehicles, although Concorde being the opposite exception.
And we talked about supersonic already.
Right. And so from subsonic, you go to transonic, right? And that's 0.8 Mach to 1.2 Mach. That's the danger zone when you have shock waves striking your vehicle, and it generally causes problems.
Yeah.
And so you don't spend a lot of time there. You try and get through it as quickly as possible. And it's actually hard to do. Supersonic, and this is the Concorde range. So this is 1.2 to as much as Mach 5. Although generally you don't see supersonic flight much above Mach 3. Yeah. Because things get complicated at that. Then you get to a realm where you're dealing more with heat than anything else.
Yeah.
And the Concorde tipped at Mach 2.5 a couple of times and actually did damage to the vehicle by going that fast. 2.2 was safer. Hypersonics is the realm from Mach 5 to Mach 10.
Oh.
That's what they generally talk about hypersonics. There is also high hypersonics, which is Mach 10 to Mach 25. And anything above Mach 25, you're now at orbital velocities on the Earth. So you're not going to be around for very long. But we do deal with those kinds of speeds when we talk about spacecraft re-entering atmospheres.
And how far up the scale do you have to get before warp drive kicks in?
Yeah, that's Mach 1000, right? Not going to do that. And I suspect you're going to burn up in just about everything. So if we talk about, the first humans to go into the hypersonic realm were the early astronauts re-entering the atmosphere.
Sure.
Right? So, Yuri Gagarin clearly first. Alan Shepard would be the first American. And while he didn't go into orbit, his trip was only 15 minutes. And this is in 1961. Right. He did go across the Kármán line, which makes him an astronaut. And his re-entry speed coming down, he hit about Mach 6.7.
Wow.
Okay. Which is fairly flippin' fast. And now you're talking the early 1960s, right? 61. So how do you keep your vehicle from melting when you're moving that quickly? And that gets into this whole concept of ablation.
Ablation, that's a medical operation, isn't it?
Ablation ultimately is material removed by vaporization or erosion, right? So you can do this with lasers. They're absolutely, there are a bunch of physical processes that you could call ablation.
Okay.
Anytime you have tissue coming away.
Got it.
But in space flight, they would create a heat shield, right? That's what this heat shield's about.
Yeah.
And in the early Mercury missions, those ones that were suborbital, the heat shield was actually made of beryllium.
Wow.
Right? It's just a metal that was really good at radiating off heat. Well, that's because they weren't going that fast. And it's not particularly ablative. What it was able to handle that heat and vaporize to let it go.
Yeah.
When they got to the Mercury orbital missions, now you're talking John Glenn and the like, and on into Gemini and Apollo, they needed a better ablator. And a good ablator is one that when it heats up, It loses material naturally. Some of that dispels, but it also starts to outgas. So it creates this boundary layer that actually reduces the heat on the shield.
Yeah.
And now we're getting into an area called plasma physics because it's so hot. The air is being pushed so rapidly out of the way that it's superheating and blowing all of the electrons off the atoms. It's ionizing the atmosphere as it goes through it. And that ionization now has some magnetic properties. And so creating a boundary layer, pushing it away, actually keeps the heat from actually overheating the vehicle and overheating the shield. What's interesting about ablative materials is that they actually have a too slow speed and a too high speed.
So they have a sweet spot.
They do absolutely have a sweet spot. It depends on the material. So and I just want to communicate this idea that how fast you're moving through the atmosphere at different altitudes matters a lot in the amount of heat you're dealing with. And how you move it away. Because if a heat shield's moving too slow, and this was a concern for the Mercury flights, it won't heat up enough that it actually creates that gas barrier to reduce the overall heating. And so it will actually get warm enough that it will communicate the heat into the spacecraft and can do damage.
So it's kind of hard. I mean, you don't just go from 0 to hypersonic. So what happens in that in the speeds between those two? Well,
and interesting, for a long time, the only time we've dealt with hypersonics is decelerating.
Yeah.
We have not been able to accelerate in that realm except with rockets.
I see.
And the more modern ablators these days are made of fancier materials. SpaceX got a very cool one called Pika X, which uses this phenolitic impregnated carbon ablator. If you really want to talk about cool vehicles in the hypersonic realm where they were repeatedly accelerating into the hypersonic realms, you still can go back to the early 60s. In 1959, the X-15.
Yeah.
Now, this was one of the X planes. They only made 3 of them, and they flew for less than 10 years, from 59 to 68. Well, they did about 200 flights in that duration. And in the time that the X-15 was flying, that's the entire Mercury missions, the entire Gemini missions, and the first flights of Apollo.
Wow.
Right. All of that happened while the X-15 was being flown.
Wow.
So, the X-15 was retired in 68. Apollo 11 lands on the moon in 69. So the explosion of research in this space from the late 50s to the late 60s, and that 10-year window is unbelievable.
Yeah, but that's when the aliens landed in Roswell. So that explains all that. Okay, next time.
There you go. And the X-15 was a rocket plane. So this is not really fancy engines. The first versions were this rocket engine called the XLR-11, which was the same engine used in the X-1, the first vehicle to break the speed of sound and level flight.
Right.
Which is interesting, right? I mean, that's how quickly this happened. And they upgraded to a bigger engine, a 57,000-pound thrust engine called the XLR-99, which was also the very first time they had a throttleable, restartable rocket engine. So we're at the beginning of all these technologies where we're already flying above Mach 5. And the vehicle itself was made out of a metal called Inconel 750, which was a nickel chromium alloy that was tolerant to high temperatures. It radiated the heat very evenly across the frame, so you didn't have any hot spots.
Right.
But the plane was too hot to touch when it landed. And now this is a rocket engine, and the downside to rocket engines is they're carrying their oxidizer with them, which means they don't have a very long runtime, literally like 60 seconds, right? Full load of fuel was 80 seconds of burn time. So in order to actually do these high velocity tests, they would carry the X-15 up to 50,000 feet in a B-52 bomber hanging underneath the wing. So the pilot of the X-15 would get in on the ground and then ride hanging from the wing of a B-52 till they got to the high altitude, about 500 miles an hour. And then you've seen the videos of this. They drop off, fire the engine, and they basically did 2 things. They did high speed runs where there'd be about 60, 70,000 feet, or they do high altitude runs. And they got up above the Kármán line, above 60 miles in certain cases. So they actually got astronaut wings. You're talking comparable altitudes to where Shepard got to in the Mercury capsule. The fastest flight ever pulled in an X-15 was one that was actually crashed. The second X-15 had a crash, and so when they were repairing it, they made it bigger. And they made it about 2 feet longer, and they added additional tanks to get 60 more seconds of flight time.
Let me guess, it crashed right after it went hypersonic.
No. Remember, this vehicle went hypersonic many times.
Oh, okay.
Right? They flew in the Mach 5 realm repeatedly, but they wanted to go faster. The problem is they were running up against the limit of what the Inconel metal could handle in terms of temperature, which is getting so hot. So they attempted an ablative coating.
Okay.
on an aircraft, which kind of unprecedented. And if you find pictures of this, and I'll include some links in the show notes, the coating, this stuff's called MA25S. It's an elastomer silicone that they troweled on to the outside of the vehicle. Apparently it took 700 hours to coat the X-15A2 with this stuff.
Wow.
So it was a little inefficient. And remember, this is an ablator, so it's going to burn off. So you have to reapply it after every flight. And so they flew it with this coating exactly once. It was in October of 1967. So you and I have just been born.
Right.
When Knight flies this vehicle up to Mach 6.7 and then comes back down, and the vehicle, it looks like a burnt hot dog.
Jeez.
He landed it. The ablation material, he had two windscreens that were split across the front of the aircraft. One of them had a shutter on it that he kept closed, and one was left open. And it was very smart that he did that, because as the ablator vaporized at that highest speed, it actually coated the windshield so that he couldn't see out of it. And it wasn't until he got down to lower speeds when he was out of fuel that he opened up the other window so he could see to land.
Wow.
They also had a prototype. This is 1967. They had a prototype scramjet engine.
Yeah.
And that engine never ran because it melted in the high-speed run.
Oh, man. Wow.
Well, and this is 1967. They were this is very experimental flying, and it just sort of points to they were able to fly that X-15 over and over again in the Mach 5 realm and had no problems. But Mach 6.7, and it just all heck broke loose.
Yeah.
So I want to convey that idea that this is remarkably difficult technology, getting up to these kinds of speeds. And one Mach higher or lower makes all the difference in the world. Now, I've mentioned scramjet. We've talked about rockets. We should have sort of run down the engines in the space here.
Okay.
Because you need different engines for different speeds.
Yeah, okay.
So obviously the rocket engine, everybody gets this, that now the great thing about rocket engines is it doesn't matter how fast you're going or where you are, a rocket engine works because it carries its own oxidizer. If it's a liquid engine, you can typically throttle them, turn them off and on. Solid rockets, once you light them, they're going. There's nothing you can do about it. But it makes it heavy. They tend to burn very quickly. And so the short burns or else they get enormous, see the Saturn V.
Yeah.
A wildly more efficient engine for flying is the turbojet engine.
Okay. Right.
And so now we're taking air from the atmosphere, compressing it, burning it with fuel, spinning turbines so we can compress more air.
Right.
Sometimes, especially in military vehicles, although Concorde had them too, we have afterburners where we actually spray fuel into the back of the engine to let that burn, and that gives additional speed.
Right.
Now, the challenge with turbojet engines is that the intake air has to be subsonic. Mm-hmm. And so for an airliner that never goes above the speed of sound, that's not a big deal. We have great big rotors. We allow subsonic air to flow into it.
Yeah.
But when you're going to build a supersonic aircraft, typically military or Concorde, you have a ramp system. And so these ramps actually restrict the amount of air that goes into the engine to slow it down enough to be able to run the engine properly without tearing it apart. And that works up to about Mach 2.5. And the problem is, as you get faster than that, the pressure on the ramps is so high, you get too much drag, you don't have enough thrust, you can't go any faster.
Yeah. Okay.
So now to go faster than that, because we know we've built aircraft that can, we have other engine designs.
And hold it right there, Richard, while we pause to pay the bills. This episode of .NET Rocks is made possible in part by Windows on the Google Cloud Platform.
You may not know this, but the Google Cloud Platform supports Windows Server 2008, 2012, and 2016.
It also supports SQL Server versions 2012, 2014, and 2016 standard, web, and enterprise editions with high availability.
You can deploy your ASP.NET Windows apps to Compute Engine or your ASP.NET Core apps to App Engine or Container Engine. That's Google's hosted Kubernetes environment.
.NET and .NET Core libraries are there for all 200 plus Google.com and cloud services in NuGet, led by John Skeet of Stack Overflow fame.
But what about Visual Studio integration? Oh, it's there. You can use Visual Studio to manage your GCP resources and deploy your existing apps.
You get stack driver logging, error reporting, and tracing support for .NET and .NET Core.
PowerShell commandlets for GCP, which run on Windows and Linux.
And a great set of partners to bring your Windows and .NET workloads to GCP, including Capgemini, Neudesic, and Magenic.
So go to gcp.netrocks.com and get your free trial today.
You're listening to .NET Rocks. This is the Geek Out with Richard Campbell and Carl Franklin. That's us. We're talking about hypersonic vehicles. So, Richard, how do we get to hypersonic speed?
So now we need some faster engines. And up till now, we've had the ramjet engine. Now, the ramjet engine is really old. It's been around for a long time because it has relatively few moving parts. You have an inlet cone that restricts airflow to, again, take the supersonic airspeed down and put a shock wave into the engine at subsonic speeds that you can then spray fuel into and burn.
Wow.
And so it's remarkably efficient. You're still using atmospheric oxygen, right? You don't have to carry your own.
Right.
And it's good. The problem is that eventually you get so fast, the shock cone can't enter the engine anymore without damaging it. Right. There's thermal problems. They start to melt.
Are there any materials that they could make the engines out of that would give them a few more degrees?
Well, and they have, and I'll talk about the SR-71 in a moment because it's sort of the coolest of the ultra-fast aircraft. Yeah. But I want to mention one more engine. And for a long time, this was purely a theoretical engine, but it's only in the past few years that it's become real. And that is the scramjet engine.
Right.
And scram short for supersonic combustion ramjet.
Okay.
And so the idea here is, let's not slow down the air so much. Let's actually allow the air to come through the engine at supersonic speeds and let it light the fuel that way, which means it has to burn really, really fast.
Right.
So ramjet engines, the sort of minimum speed for them to work when you have a good shock cone is around Mach 3. You can make lower speed ramjets, but then they don't go faster, and the goal was to go faster. Scramjet engines don't seem to be able to light them much below Mach 4, closer to Mach 5. Now, but there's not a lot of experience with scramjets, and I'll talk about this as we get more into the research part of all of these things. But we would not be doing service to understanding the complexities of hypersonic flight if we don't talk about the most famous supersonic airplane of them all, the SR-71.
Right. And we've talked about this before. It actually expands during flight.
Yeah.
It's
crazy. All vehicles, everything in the supersonic and hypersonic realm is about managing heat.
Right.
Right. That is the problem. Heat all the time because heat damages the metal, which makes it less structurally strong.
Yep.
The SR-71, which is an ancient airplane, first flight 1964.
Yeah.
Was basically made out of titanium.
Yeah.
And in fact, this is during the Cold War. This was a Cold War vehicle. The Americans didn't have a lot of titanium. They actually bought most of their titanium from the Russians.
Yeah, yeah.
They did it secretly through shells companies. Because if the Russians had known, they would not have sold it to them.
Right.
The windshield had to be made out of quartz because it got so hot.
That's crazy.
But the plane's enormous, right?
Yeah.
120 feet long. This is a big machine. And that J58 engine is what we call a dual cycle engine. It has both a turbojet and a ramjet engine combined.
Wow.
And that's how it was able to take off from the ground, is the turbojet would allow it to fly, to take off like a regular airplane and accelerate up to supersonic speeds.
The ramjet takes over after that.
Yeah. So and that's exactly right. There's a computer, initially an analog computer. That's how old this stuff is.
Wow.
In the 1980s, they switched out with a digital one that would move the inlet cone spike to create the correct airflow into the engine to allow them to use the ramjet mode above the speed of sound.
Wow.
And some aspects of the SR-71 to this day are still classified. But the plane was designed to cruise efficiently, as in the most fuel-efficient operating mode for that engine, Mach 3.2.
Oh, man.
And in fact, as it got faster, they went faster than that, although they've never admitted how fast, it burned less fuel for every mile that it traveled.
Whoa.
Because you're going so fast. And the actual limit on the engine, again, was heating. They were talking about pushing 800 degrees Fahrenheit, over 400 degrees Celsius.
Wow.
That the engine themselves were glowing hot, almost transparent, because they were so hot, ripping through the air at those kinds of speeds.
That's nuts.
Well, and it needed a special kind of fuel. So normal jet fuel that you use in a regular airliner, they call JP1 for, jet fuel 1. This was called JP7, and it was a very high temperature fuel because the plane got so hot. If the regular fuel would literally spontaneously combust, then that would be bad.
Yeah.
So they had to make this heat-resistant fuel. And the story goes that JP7 was so heat-resistant, you could drop a lit match in it and it wouldn't light.
Yeah. Yeah.
Because we had no high volatiles in it. So
Crazy.
it was a very, very stable fuel. And of course, the story, most people know about Blackbird, this was a spy vehicle and it never got shot down. They did lose 12 to various accidents out of the 32 were built, but it was never shot down because anybody who ever fired a missile at it, they just accelerated away. Originally, they built it to carry a drone to do the reconnaissance, and then they realized the plane itself could do the reconnaissance, so they stopped trying to use the drone. The drone was dangerous anyway. And NASA flew, in the 1970s, they flew a prototype of the SR-71 called the YF-12 for doing high-velocity experiments. And then when the Air Force stopped using the SR-71 in the 90s, a few of them went to NASA again. They continued to do high-speed research with them.
Wow.
So it's not actually a hypersonic vehicle, but I wanted to introduce a few concepts. One is we did have a bunch of experience with the challenges of temperature and materials at these very high speeds. And we have built combined cycle engines.
Yeah.
Because every bit of evidence shows if we're going to get serious about this, making hypersonic vehicles, we need combined cycle engines.
And, the concept of a hybrid engine is not new, and it certainly came around again in the hybrid car idea, where you want to use the electricity to get your torque, because that's where, from 0 to whatever, 30 miles an hour, that's where a gasoline engine is less efficient. And certainly you can get a lot more torque from electricity at that lower level.
And ultimately compression engines like a gasoline engine have an ideal running speed that's the most fuel efficient, and using that to turn a generator, generate electricity may actually be a more efficient way to make things work.
Yeah.
The downside, of course, is you lose a certain amount of performance there, and you're carrying two engines around.
Right.
So things are heavier, more complicated. You're trying to be simple here. You don't want to carry multiple engines, but you don't really have a choice.
And I know we've said it before, but the SR-71 expanded like 11 inches during flight?
Something like that.
Stretched.
Well, and the famous thing about them is rather than make tight-fitting fuel tanks, because when it got that hot, they would actually crack.
Yeah.
They used corrugated metal so that it leaked when it was on the ground.
Wow.
And then as it heated up, it sealed up.
Wow. Well, Richard, guess what time it is?
It must be that happy time again.
Yeah. It's time to stretch the limits of humor more than an SR-71 at Mach 3.5.
At least it didn't have any leaks.
Yeah, you know what? Because I said more than an SR-71, so it might have sounded like a metaphor, but it's not. It's a simile. Simile is like a metaphor. Metaphor is a metaphor, but a simile is like a metaphor. You understand?
Yeah.
Okay.
It is grammar school humor. That's what that is.
No, it's still funny. To me, anyway. I don't know. It's actually time to give away a D-Experience subscription from Developer Express to one lucky member of the .NET Rocks fan club. Become a UI superhero with DevExpress UI controls and libraries, and deliver elegant .NET solutions that address customer needs today, and leverage your existing knowledge to build next-generation, touch-enabled solutions for tomorrow. Whether it's an Office-inspired application or a data-centric analytics dashboard, DevExpress Universal ships with everything you'll need to build your best without limits or compromise. Learn more and download your free 30-day trial at devexpress.com/superhero.
All right, buddy. Who's our winner?
Today's winner is Taya Lisaki.
Oh, congratulations, Taya.
Congratulations, Taya.
Golf clap for you.
Yeah. Taya just won Developer Express's D-Experience subscription, a huge pile of awesome from our friends over there, just for being a member of the .NET Rocks fan club. And if you don't know what that is, go to .NETRocks.com, click on the big Get Free Stuff button, answer a few questions, and join the fan club. We have thousands of members all over the world. In every show, we like to give away stuff from our sponsors. And every December, we give away a $5,000 technology shopping spree to one lucky member of the .NET Rocks fan club. But you got to sign up to win. And Richard, before we get back into it, we haven't asked each other, what's on our technology shopping list lately. You have anything neat that you've seen that you're really interested in?
If it was just $5,000 out of the blue, I probably would get a Surface Studio.
Yeah.
Just because I can't justify that money myself. So for an indulgence, that's something to experiment with. But you know me, I've got most of the gadgets.
Yeah.
And you, sir?
I don't know. I'm looking at 4K video cameras. They just keep getting cheaper at the prosumer level and with more features and things that, it's just like too good to ignore, especially if you're doing films and things.
Yeah, we are really getting to an interesting state in cameras and stuff.
Yeah.
And I'm fascinated to see whether the 360 slash 3D, like 360, basic 360 cameras are fine.
Yeah.
But the full 3D ones as well, the math on those is crazy complicated. But these are all things to try and make VR come true.
Yeah.
You could spend a lot of money there.
Yep.
Very gadgety.
So continuing down the line of different aircraft that approaches hypersonic, you were going to talk about the X3?
I was going to talk about the X-30. So I want to fast forward you a little bit, Cold War stuff towards the end of the Cold War in the 1980s. Okay. And DARPA, that's the Defense Advanced Research Projects Organization.
Yep.
Now, these are the guys that brought you the internet.
Yeah, right.
And a whole bunch of other things. They had a project in the 80s that was codenamed Copper Canyon that was really talking about, do we have the materials now to be able to build an ultra high speed vehicle? Now, this ended up tying into the Space Defense Initiative, which was nicknamed Star Wars. This is the Reagan era. And one would argue these were the moves that forced the collapse of the Soviet Union as they continue to raise the bar on more and more advanced technology.
Yeah.
And in the 1986 State of the Union speech that Ronald Reagan gave, he announced this thing he called the Orient Express, which was really the X-30, the idea that that America was going to build a vehicle capable of flying into orbit 2 hours from LA to Tokyo, that kind of concept.
Right.
And the Soviet Union immediately responded that Tupolev would be developing the Tu-2000 strategic bomber, a hypersonic strategic bomber. So that was still the Cold War battle. And we know how this ends, right? By 89 to 91, all of this unravels. So the X-30 persisted for a while. The test vehicle was going to, in theory, be a single stage to orbit. Initially, would just be an ultra high speed airliner. This would only be a 2-person vehicle, 160 feet long.
Yeah.
With about 74 feet wide, 300,000 pound vehicle. So we're talking the size of a B-52 bomber, although more wedge shape. It looks more like a doorstop than anything else, with essentially no wings, just a lifting body.
Wow.
And the only thing they talked about in terms of an engine was a scramjet.
Okay.
And since I've already explained to you that scramjets don't even light till Mach 4, I just think they were a bit diluted. But this is the 80s.
Right.
I'm never really sure how serious they were about this, but they developed a bunch of technology. So the first contracts came in 86 around Reagan's announcements. The construction of a test vehicle started in 1990. By 93, they canceled it.
Okay.
Of course, at this point now, the Soviet Union has collapsed. There's sort of a swords into plowshares movement. This is the Clinton era.
Right.
And so they're sort of winding those things down. But a bunch of interesting technology did get developed. One of them was building composite fuel tanks. The X-30 was proposed to fly using quote unquote slushy liquid hydrogen.
What?
So liquid hydrogen cooled so cold that it was crystallizing, that there were chunks of frozen hydrogen in it.
Wow.
And I would just like to state for the record, that's been done in the lab. It's never been done anywhere else. It's incredibly difficult to get hydrogen that cold. So again, remarkably optimistic design concepts here.
I'm just curious about the properties of cold hydrogen. Is it more or less flammable?
It's not that particularly flammable, but it's very hard to stay that cold.
Yeah.
The biggest problem you have with liquid hydrogen in general is what they call hydrogen embrittlement.
Yeah.
It damages all the materials. It's one of the reasons that folks like Elon Musk stay away from liquid hydrogen. Like he said, no liquid hydrogen, just because it adds so much expense to everything you do to manage a super cold fuel like that.
Well, when the age of hydrogen vehicles was going to take over, remember that a few years ago? And was it sort of the same idea that just transporting and dealing with hydrogen turns out to be a lot of expense?
Well, you go down the liquid route and to get denser, and then you have all of these problems, or you go with the compressed route and then you don't have enough power per pound, so to speak. right? It's one of the chemical combinations of hydrogen made more sense, right? There's other ways to hold on to hydrogen, but in the end, it just wasn't practical.
Right.
And electricity seems to be winning the day.
Yeah.
I got to finish the conversation on the X-30 from the point of view of even when these things get shut down, technology from them carries forward.
Yeah.
So, another show we'll probably do coming out of this is single stage to orbit, because X-30 was proposed as a single stage to orbit vehicle.
Okay.
And when the X-30 shut down, some of the technology showed up in a thing called the X-33, which was going to be a technology demonstrated for single stage to orbit that would eventually be called Venture Star.
Okay.
Canceled by 2001. Nothing ever came of it. That's why you've never heard of it. But there was another project that was basically a shrunk down version of the X-30 called the X-43. And that was a NASA hypersonics program in the early 2000s. Now, at the same time, our friends at DARPA, who had originally proposed Copper Canyon and that led to the X-30, proposed a new project. This is in 1997, so it's a few years on.
Okay.
This project was called Prompt Global Strike. It's such a happy name, really.
Yeah.
But what they're really describing was giving the United States the ability to hit any target in the world within an hour with conventional weapons.
Okay.
Now, this is after the 1991 Desert Storm War, which I think was the war that really showed that nuclear weapons were obsolete.
Yeah.
You know, because that was a televised war. Remember Arnold Schwarzkopf and, putting missiles through windows.
Right.
Like being able to be super precise. It's like there's no target we can't destroy with conventional weapons. We just don't need nuclear weapons anymore. Not that we've ever gotten rid of them,
right,
but that we were capable of doing this.
We also saw the Patriot missiles, which supposedly were shooting down missiles that were being lobbed at us, although the jury is out on whether most of them hit their target or not.
How well they worked for that. Because that's not what Patriot was built for. Patriot was built to shoot down aircraft, not missiles.
Yeah.
So, but that also kicked off this whole missile defense program. All of those things come from this. And I'm sorry that so much of this is military, but it's sort of the reality of exploring these extreme regimes is the realm of the military.
Yeah.
However, NASA, still a civilian organization, with the X-43, they now, instead of building this 160-foot long vehicle, it was a 12-foot long vehicle.
Yes.
Little. 3,000 pounds.
Yes.
3.5 meters. You can put it in your pocket. It's cute.
Yeah.
But what they're trying to figure out is, can they make something that will actually accelerate at hypersonic speeds? Now, it's because it's just a small vehicle, they mount it to a rocket and carried it with an aircraft up. So this is in 2001, they do the first attempt to fly this thing. It's actually off an L-1011, which is an old tri-jet airplane built by Lockheed.
Yep.
Very similar to the DC-10, with this Pegasus rocket hanging underneath of it, and the X-43 stuck to the front. Now, the first flight in 2001, not a happy thing. The booster rocket failed, so they never even got a chance to test the thing. Lost it all.
Yeah.
In the second flight in 2004, so 3 years later, the Pegasus rocket actually boosts the X-43 to 29,000 meters. That's 95,000 feet.
Wow.
So that is way up there.
Yeah.
And moving at Mach 7. So it's already at hypersonic speed. The rocket drops away. The engine fires up on the X-43, and the engine only lasts for 11 seconds. That's all the fuel they have. Remember, it's only a 12-foot long vehicle. It's just not that big.
Right.
However, it does maintain its speed.
Wow.
It travels for that 11 seconds, 24 kilometers. Right, because it's moving so
pretty
fast.
freaking fast.
That's the thing that's hard to get in your mind when you're talking about speeds of that kind of thing. 15 miles in 11 seconds.
Well, you said 24 kilometers, right?
Yeah, that's 15 miles.
15 miles, yeah.
In 11 seconds.
Yeah, that's pretty amazing.
So it had actually, this is the first time that a scramjet engine had lit at hypersonic speeds and had accelerated the vehicle. So that mission achieved the test goal. And so on the third flight, which is the same year, in November of 2004, they actually got it up to Mach 9.6.
Oh my God.
And at Mach 9.6, it couldn't accelerate anymore. That was the cruise speed of this vehicle, which is really, interesting. And at that point, they proposed a new model of the X-43 called the X-43C. It was going to be bigger, more powerful, and ultimately was shut down to make an entirely new X project called the X-51. So the X-51 doubled the size of the X-43. It was 25 feet long, much bigger vehicle. And it took several years to get this thing together. Its first flight was in May of 2010.
Yeah.
So we're getting up to pretty current times. The first flight did not work well. Actually, the first 3 flights didn't work well. The first flight was a test flight. They ran it at Mach 5. So not really an achievement, but it worked. Second flight boosted up to Mach 5, and now they're trying to test a larger scramjet engine, and that's challenging. And so the engine actually has these 2 stages. This is what they call a Pratt & Whitney SJY61 scramjet. It's a great name.
Ooh, yeah. Very official.
Now, the challenge with scramjet engines, remember, you're going to try and light an engine while moving at Mach 5. You're not really going to slow down the air. No subsonic airflow, right? Again, you have heat problems. So they're using JP7, the same fuel that the SR-71 used. But you can't just light that fuel. So they actually have a pre-light mode. They use ethylene, which is a flammable gas, to start the engine. Once it's running on ethylene, they switch to the JP7. So in the second flight, they lit the engine with ethylene, but it did make the transition to JP7. Failed.
Okay.
Third flight, August 2012. They get it up to Mach 5. It immediately loses control, crashes in the ocean. Bummer. Now, the fourth flight. This is the good news. This is May of 2013. The B-52 drops it off at 50,000 feet, so 15 kilometers up. It's moving at Mach 0.8. The booster rocket fires, boosted up to Mach 4.9 at 63,000 feet. The scramjet lights with ethylene, then switches to JP7. It now accelerates and climbs up to Mach 5.1 at 64,000 feet. It runs for 3.5 minutes, 210 seconds. In that time, it travels 227 miles, 364 kilometers.
Yeah.
So it was a validation of the entire model that this is a working engine.
Wow.
And then they shut it down. So interesting. And one of the things I've come to appreciate with the American military, they're pretty happy to talk about what they're doing when stuff doesn't work.
Yeah. But
as soon as it does, they get really quiet. So once that X-51 did its thing, they just stopped talking about it. There's a proposed project called the High-Speed Strike Weapon that's supposed to be fielded in the 2020s. So I suspect that the U.S. has now got a black project developing a working hypersonic cruise missile.
Wow.
They just don't talk about it anymore.
And you think this because?
Because the pattern is fairly consistent. When technology isn't working and still being developed, they talk about it. The scientists do anyway. And the reason they do is because they need to keep getting funding.
Yeah.
We achieved this goal. We didn't achieve that goal. If we get more money, then we'll continue to do this thing. But once you've achieved your goals in a way that shows the thing absolutely works, you get funded. And when you get funded, you don't need to talk anymore.
Yeah, yeah.
So I suspect that all of that went quiet because they're now working on a final product, right? I mean, we were only talking a few years ago, right? That last flight was in 2013, and this technology takes a while to develop, but it looks like the United States has a working scramjet engine up to a certain size, 25 feet long and 4,000 pounds empty. That's cruise missile size. So that could be a weapon.
Wow.
There are other hypersonic developments going on in the military. There was a project called, as also part of Prompt Global Strike, the Force Application and Launch from Continental United States, the acronym being Falcon. Okay, save me.
Yeah.
But these were actually what they called hypersonic cruise vehicles. So rather than focusing on engines so much, they were actually doing maneuvering. So the idea here is, when you think about Prompt Global Strike, you say, well, hey, don't we have ICBMs? Like, why are we doing this?
Right. Are they cheaper?
Well, the problem with ICBMs is they have a very consistent ballistic trajectory. They can't maneuver very much. And so you can kind of see them coming. And because they're generally recognized as carrying nuclear weapons, using them upsets people. They tend to throw nuclear weapons back at you just in case.
Yep.
So they don't want to use them. So they're trying to come up with a cruise missile that's a little subtler and quicker and not recognized as a nuclear weapon carrier, because they really don't need to be nuclear weapons anymore. So DARPA and this whole series on the military, they built a bunch of different experiments to test what they call this hypersonic glide vehicle.
Yeah.
But in the meantime, let's get back to sort of some non-military ideas.
Okay.
So DARPA proposed a thing called the Advanced Full Range Engine, or AFRE. So they're trying to figure out, how do we build an engine so that you can take off like an airplane and go up to hypersonic speeds? And their goal was to go from 0 to Mach 6 and back without dropping anything. Because if you think about everything that's been tested up till now, it's always had rockets that were dropped off the back. Yeah. And that's fine for a military weapon. Nobody's going to blink at that on the military side. You can afford to essentially spend that money.
Right.
But if you're actually going to make it into something useful for other things, this is the kind of engines we need to build. And the developments, it's funny how the names change when they start to understand how to do stuff now. So you don't see scramjet so much anymore. Now you see things like dual mode ramjet combustors.
Wait, does Microsoft have anything to do with this project? Because
I tell you, the military is probably where Microsoft gets their cues from for some of these things. The
multi-syllabic product name.
These crazy names.
Yeah.
A dual mode ramjet combustor, by the way, is a kind of scramjet engine that has multiple fuel injectors in different locations within it based on the speed of the airflow going through the engine. So as you go faster, they actually you put fuel in different places and use the shock waves to still combust the fuel. So it's what they've learned actually making these things work.
Wow.
And now you get into the bigger combination. That's AFRE is one set of research that's going on right now to try and make these engines more effective. But there are other organizations, including other countries, that are proposing these things as well. So the Russians have sort of gone toe to toe with the Americans on developing some of this stuff. They're working with the Indian government on a vehicle called the BrahMos 2, which is supposed to be a Mach 7 hypersonic cruise missile.
Okay.
Nobody really knows if it works. There's also the Russian KH-90, but the Chinese have popped up now, showing demonstrations of hypersonic light vehicles and so forth. And they recently held, and this is one of the catalysts for me to do this show, they held a conference in March of 2017 called the International Spaceplane and Hypersonic Systems and Technology Conference. This is in Xiamen. And they showed off all the research they've done over the past 10 years, including scramjet engines they tested in 2015.
Wow.
And they proposed their own concept of a combined cycle engine. So let's talk about a few different combined cycle engines.
Sure. So how many types of combined engines are there?
Well, there's really only 3, maybe 4 things you'll want to combine. There's the turbine engine, right? That's the thing that's going to get you from 0 to Mach 1 something.
Yep.
There is the ramjet engine. There is the scramjet engine. And we're seeing rocket engines show up here and there.
Okay.
Which we don't like rocket engines because they're inefficient, but it's kind of trying to fill the gap. So you'll see these things like rocket-based combined cycle engines.
Okay. So
a ramjet and a ducted rocket engine together, or turbine-based combined cycle engines. In 2008, Aerojet Rocketdyne proposed an engine, which has kind of been rekindled recently around a project that Lockheed Martin's talking about called the SR-72.
Really?
Yeah, the SR-72 name annoys me because, of course, they're playing against the SR-71. Sure. It's another supposed skunkworks project, although they really have no funding for it.
In other words, nobody knows what's really going into it.
I don't know that anything in this is real, and that annoys me. Okay. But the specifications around this engine, which they call a trijet engine, because it has 3 different engines in it. So it has a turbine engine.
That'll get you off the ground.
Right. Then it has 2 different kinds of ramjets. One called an ejector ramjet and one called a dual mode ramjet. Now, the ejector ramjet we've really never talked about before, and it's actually tough to do research on this because everybody has a different name for this concept. But here's the clever idea. So this is a ramjet engine. So again, basically no moving parts. Right. The ejector part is that they put small rocket nozzles at the front of the duct. Now, why in the world would you put little rockets in there?
Yeah, I don't know.
They're burning peroxide. So there's a really cool chemical engine. You remember the rocket pack? You know, the James Bond, you put on this backpack, you got 2 little handles and you take off.
Yeah, exactly. And we all wanted it.
Yes, but it's only got a runtime of like 60 seconds. Right. So, and if you're up in the air at the 60-second mark, you're about to have a really bad day.
Not a good idea.
So the rocket involved in that is a peroxide rocket motor. So you take this high test peroxide, which, by the way, is very dangerous stuff.
Sure.
And when you pass it through a silver catalyst, it separates and comes out of a nozzle at high speed.
Sure.
What it separates into is oxygen and water. So by running these rocket nozzles at the front of the duct, you're actually providing a little bit of thrust, but you're also dumping a whole bunch of oxygen into the inlet at speed, which you then inject fuel into and burn.
Okay.
That's an ejector ramjet.
All right.
The dual mode ramjet I've sort of talked about already. The multiple injectors based on speed. This is sort of a scramjet model. So here's the sequence with these three different engines.
Okay.
From 0 to Mach 1, the doors on the turbine engine and the injector ramjet are open. The turbine's providing all the thrust from 0 to Mach 1. So that gets you off the ground, gets you to altitude, you break the speed of sound. As you get above Mach 1, the turbine doors are gradually closing. Now, there's ramps on there to control the airflow anyway, so it makes sense that they're closing. But by Mach 2.5, the turbine is shutting down, and you're running purely on the ejector ramjet. Now, you're probably injecting less peroxide at this point, so you're probably turning that down as well.
Okay.
Your ejector ramjet now accelerates you from 2.5 till a little past Mach 3. Around Mach 3, you can start running the dual mode ramjet. Now, the dual mode ramjet doesn't have doors on it because it's just an open duct, basically. So you have a combined thrust from the ejector ramjet and the dual mode ramjet until you get up above Mach 4. Above Mach 4, you close off the ejector ramjet and you do everything out of the dual mode ramjet up to as fast as you need to go.
Okay.
Complicated, huh?
Yeah.
And think about all the different fuels we need here. So we need JP1 for the turbine.
Which is?
That's regular jet fuel,
okay.
Right? You need some peroxide for those injectors. You need some kind of rocket fuel for the ramjet. That could be JP1, or it might be a higher temperature fuel. You definitely need a higher temperature fuel for the dual mode ramjet as things get hotter, and that's probably JP7.
Right.
So we're talking 3, 4, maybe 5 fuels.
Yeah.
It's a lot of tanks. It's complicated.
Yeah.
It's expensive.
Yeah.
The Chinese proposal, and this comes out of the papers from March 2017, is a rocket design. Again, translation may have trashed this. Turbo-aided rocket-augmented ram/scramjet.
Oh, boy.
Right. So RP1, or jet fuel for the turbine. Also RP1 and liquid oxygen for the rocket. So they're running a regular rocket engine to do the accelerations at certain points, and then RP1 for the scram and ramjet. Mm-hmm. This is, I don't know if this is actually flown. I think it's a tested design, untested design. So you use your turbine to take off. You get up to Mach 2 with that using a low speed duct and RP1. Now, you've got to get fast enough to be able to switch over to ramjet mode. So you fire these rockets inside of the duct with your supply of liquid oxygen to accelerate you off above to Mach 3, shutting down the turbine engine in the meantime and engaging the ramjet engine. So the rockets then are only used when you have to get up to that higher speed, and then you switch over to the ramjet, gradual transition to scramjet above Mach 6.
Okay.
I hate carrying liquid oxygen around, but you only need it at certain times, so it kind of makes sense. Yeah. But it's interesting to just see how far along they are with those particular designs.
Wow. Fascinating.
Let me throw one other, I remember I was reading a bunch of papers.
Yes.
So I talked about ablators.
Yeah.
The problem with ablators, of course, is that they ablate, so you can't reuse them.
Right.
But there are other ways to manage heat at ultra high speeds. And we can look back all the way to the 70s to the space shuttle for this, right? Those silica tiles, they don't ablate. Mm-hmm. They actually are able to handle very high heats. They distribute the heat. They're a thermal distribution system for heat management. Right. And those have been improved. The 1970s version had problems. They were quite brittle. They fell off. Ultimately, the leading edges needed more stronger heat systems, so they used a thing called carbon-carbon, which led to the loss of Columbia because they were so brittle.
Right.
More modern versions of those complex silicates have been developed, and they handle the heat better and better.
Yeah.
One of the papers I read from 2016, again, Chinese translated letter, was a thing called magnetohydrodynamic heat shielding.
Oh, wow. You throw these terms at me, I try to come up with any sort of understanding from the name. It's very hard.
Absolutely. So let's go.
Magneto means magnetic, right?
Magnetic hydrodynamic.
Hydro is water.
Although in this case it's not water, it's plasma.
Okay.
So again, we're traveling at ultra high speeds, right? Mach 5 plus. We're in the hypersonic regime, which means that the air in front of our vehicle is being turned into a plasma.
Whoa.
Because we're going so fast.
Whoa.
And it's the problem with plasmas is they tend to rip up the atoms of your vehicle, and you don't like that, right?
Right.
You want to get the plasma away from your vehicle. And that's what those ablators do, because the ablators, as they heat up, as they pyrolyze, they push out gas to push the plasma off of the heat shield.
Man.
What they're proposing here is using superconductive magnetic coils to actually take advantage of the magnetic sensitivity of the plasma to push it off of the vehicle.
That's incredible. You know, it all starts with levers and pulleys, man. we started with levers and pulleys and we got to this.
Yes. Now, this was a scientific paper that was showing that if you build these kinds of magnets, you can push that plasma field away from the vehicle up to 20 times further than the natural shock wave. So the heating goes down dramatically. The problem is that superconductive magnetic coils need to be super cooled.
Yeah.
Right? They need liquid helium, maybe liquid hydrogen if you have high temperature superconductors. You know, the other side of that is still thousands of degrees. Yeah. So this is going to be a very challenging heating regime. And with superconductive coils, as soon as they get too warm, they stop superconducting. They don't work anymore.
Yeah. Yeah.
That would be an abrupt collapse of that protective field that would now be pressing against the vehicle.
There's that sudden stop at the end.
No, yeah. The rapid unplanned disassembly is what you're talking about.
Rapid unplanned disassembly. I like that.
Very rapid. Here's a crazier idea for you. You can shape that plasma. So not just push it away from the vehicle, but make it closer or further away on different parts of it to not only protect the vehicle, but reduce drag.
Sure.
And be able to maneuver the vehicle magnetically.
You could eject the plasma core to...
Oh, look. Star Trek references.
We eject the plasma core.
Now I think you're supposed to eject the warp core.
Well, yeah, but there's something about plasma in there too.
Yeah.
I don't know.
But if you're you've got this plasma field in front of you, you're using a magnet to keep it away from your vehicle so it doesn't damage it. Now you shape it so that you create more drag or less drag in different areas. You can actually maneuver your vehicle with the magnetics.
Wow. That's crazy.
It's very interesting stuff.
And you're going so fast that you don't want to be off by 1 degree.
No, you want to be able to do that very precise control. Yeah. And you have a problem with flight surfaces in this regime as well, because as they push into the airflow, they're going to heat up more. So magnetic maneuvering might actually make more sense.
Yeah. Wow, it's crazy.
So we're in an interesting time now. You know, we're getting a lot further along. I want to bring up one other technology that we have talked about previously, but in the context of these developments, they may actually make more sense. Remember when I talked about reaction engines?
Yeah.
And their synergistic air-breathing rocket engine, the Sabre engine?
Yeah.
And that was the idea of having a rocket engine where it's condensing liquid oxygen in real time through an inlet.
Right.
And in fall of 2016, the United States, this is a British company, right? Reaction Engines, the UK company, put money in to develop a jet fighter sized version of the Sabre engine. They figure about a 44,000 pound thrust engine, comparable in size to the kind of rocket engine, the kind of jet engine you'd see in the F-35.
Yeah.
In the context of these kinds of vehicle concepts, that engine might make sense. So I wonder if that's part of the plan here.
Time will tell.
And if we can the bottom line is I believe the scramjet engines now exist and function, and we can get better at them. That sort of opens the door to, can you get into a vehicle that could fly all the way into orbit? And maybe we should make another show around that. Maybe we should. This is fascinating stuff. Yeah, I'm excited about it. It's very interesting. I mean, it's frustrating that it's all a lot of it's military driven, but it could. We talk about reducing cost of access to space. You know, all the stuff that Elon Musk is doing. Being able to take off like an airplane, fly into space, and fly back is going to involve much of the technology I've just described. Yeah. Good stuff. Thanks, Richard. It's always a pleasure talking to you. You bet, buddy. Good fun. And if, folks, if this is a show you like, please give us a comment. Let us know what you like, don't like, concerns you had. Do you want to do single stage to orbit or any other show ideas? We're all ears. Yes. All right. We'll see you next time on .NET Rocks.
.NET Rocks is brought to you by Franklin's Net and produced by Pwop Studios, a full-service audio, video, and post-production facility located physically in New London, Connecticut, and of course in the cloud. Online at pwop.com. Visit our website at dotnetrocks.com for RSS feeds, downloads, mobile apps, comments, and access to the full archives going back to show number 1, recorded in September 2002. And make sure you check out our sponsors. They keep us in business. Now go write some code. See you next time.
Got transmitter banned by the FCC. Yes, I'm a